Hello, everybody. We're going to continue our lecture for chapter 3. In last lecture, we have talked about the Laplace equation. And here, we're going to start talking about some solutions for these equations, including the boundary condition. Because the boundary condition um, can help, actually, it's necessary to solve the Laplace equation. And another thing we're going to talk about is the uniqueness of theorem. Okay. Laplace equation doesn't by itself determine the potential V. In addition, suitable boundary conditions must be supplied. So you have to use boundary conditions to solve the Laplace equation. Okay. So if we need to use the boundary condition to solve this Laplace equation, then there's a question. What are the appropriate boundary conditions which is sufficient to determine the answer and not so strong to generate inconsistent or redundant? So the one-dimensional case is easy because for one-dimensional Laplace equation, you have a general solution, which is V equals to mx plus b. So in this equation, it's an equation for a line. So to determine the equation of a line or determine the specific solution for your Laplace equation, which is this line equation, then you need two, let's say, you need two specific solutions or values. So we need specify the values of the function at each end, means totally you need two set of values of v and x. Then you can determine m and b, which means you determine the line equation, or you determine the specific equation for your Laplace equation. So I think everybody is familiar with this equation, the line equation. If you get two specific set of values, then you can solve the equation. You will get m and b, then you get the line equation, or the general or the specific solution for your Laplace equation. Okay, but if you get three set of values of v and x, things becomes more complicated. For two of the values, you get the specific solution, but if you have three of the values, either they could be redundant, or in a worst case, you might get some inconsistent set of values, which doesn't help you to determine uh, uh, the constant of m and b. Instead, it gets some inconsistent, and you figure out you can get a unique value for m and b. So that means in this equation or in this solution, you just need two values of v and x to determine the specific solution. Those two set of values could be considered as the boundary condition at the line. Let's say if this is a line, v equals to mx plus b. If you get two set of values at two ends, then that could be considered as its boundary condition, because you know the values at the boundary and the boundary here. For a line, the boundaries are the ends. So from this one-dimensional case, it tells us that if you know the boundaries for a line equation, then you will be able to determine the unique solution or unique line here. Okay. In 2 or 3-dimensional cases, we're confronted by a partial differential equation, which becomes more complicated. And it's not so obvious that would constitute acceptable boundary conditions. In the shape of a rubber membrane, if you remember in our previous lecture, we draw um, a box and we put a rubber membrane on the box, and the boundary of the box could be artificial shape. If we take this as example, the uniquely determined by the frame over which is stretched, like or like a scanning jar lid, can it snap from one stable configuration to another? Actually, the answer is the V is uniquely determined by its value at the boundary, and the scanning jars evidently do not obey Laplace equation because the uh, scanning jars um, is not the, let's say, the smallest uh, surface area due to the boundary condition. If it's the smallest area, the scanning jar cannot, um, let's say, cannot snap from one stable configuration to another. So, um, however, other boundary conditions can also be used, and we will see it in the problem 3.5. The proof that a proposed set of boundary condition will suffice is usually presented in the form of a uniqueness theorem. There are many such theorems for electrostatics, all sharing the same basic format. And now let's see the most useful ones. Here we'll show two of the uniqueness theorem. So the first uniqueness theorem is the solution on Laplace equation in the same value V is the same volume V is uniquely determined if V is specified on the boundary surface S. Now let's see this case. And let's prove this theorem. In this figure shown below, we have drawn such a region and its boundary. There could also be island inside, so long as V is given to all their surfaces. Also, the outer boundary could be at infinity, where V is ordinarily taken to be zero. Suppose there were two solutions to the Laplace equation. Okay, for such a boundary, you have its general solution, which is this V. And let's say for the general solutions, if you use the boundary conditions, you can generate two different solutions. Let's say they're V1 and V2. So this is solution 1 and this is solution 2, both of which assume the specific value on the surface. So now let's prove that they must be equal. The trick is look at their difference. Now let's see V3. Let V3 equals to V1 subtracted by V2, or the difference between V1 and V2. And notice that the V3 must obey Laplace equation 2. So V so V3, um, let's say the del squared V3 equals del squared V1 subtracted del V squared V2 equals to 0, because V3 itself is a solution of this Laplace equation. So at the boundary, so they share the same boundary condition, and itself is a Laplace equation, so it should also obey the Laplace equation. So the del squared V3 equals to 0. And it takes the value 0 on all boundaries, since V1 and V2 are equal there. Because at the boundary, V1 and V2, they share the same boundary. So V1 and V2 are the same at the boundary. So at the boundary, V3, let's say V3 the boundary is 0. And Laplace equation allows no local maxima or minimal. Then all extrema occur on the boundaries. So the maxima and the minima of value V3 are both 0. Therefore, V3 must be 0 everywhere. Let's say if you have a boundary of V3 and at the boundary you have 0 values everywhere on the boundary, then if it's 0 and everywhere on the boundary and there's no minima or extrema, or there's no local minima or local maxima all over the entire let's say region, then you have to have 0 everywhere. Otherwise, let's say if you have some uh, position close to the boundary which is non-zero, which is 1, then there must be some maximum or minimum values found in the entire region. So it has to be all 0 everywhere in this region. So V3 should equal to 0 everywhere. If V3 is 0 everywhere, that means V1 subtracted by V2 equals to 0 everywhere, means V1 and V2 have no differences. So V1 equals to V2. Then we proved that the uniqueness theorem, which is the solution to Laplace equation in some volume V, is uniquely determined if V is specified on the boundary surface. So let's keep it in mind. If you have a Laplace equation and you specify the boundary values, then your solution for the Laplace equation is unique. And the uniqueness theorem is a license to your imagination. It doesn't matter how you come by your solution. If, let's say, A, it satisfies Laplace equation, and B, it has the correct value on the boundaries, then it's right. Then the uniqueness theorem is always right. You will see the power of this argument when we come to the method of images in next lecture. Incidentally, it's easy to prove the first uniqueness theorem. We assume there was no charge inside the region in the equation, so the potential obeys Laplace equation. But now let's see a more complicated case. We may as well throw some charges in the region that you considered, and then it becomes Poisson equation. And the argument is the same, only this time, instead of Laplace equation, now you have a Poisson equation. It's not 0 on the right side. Instead, you have an equation of charge density. So in this case, the potential on the volume V is uniquely determined if A, the charge density throughout the region, and B, the value of V on all the boundaries are specified. So let's just remember this conclusion. And here, conductors and second uniqueness theorem is shown here. For example, the simplest way to set the boundary condition for an electrostatic problem is to specify the value of V on all surfaces surrounding the region of interest. And this situation often occurs in Laplace. In the boundary, we have conductors concept to connected to batteries, which maintain a given potential, or to ground, which is experimentalist word for V equals to 0. That's the boundary condition. And there are some other circumstances in which we do not know the potential at the boundary, but rather the charges on various conducting surfaces. If we put charge QA on the first conductor and QB on the second conductor, and so on, the charge distribution on each conductor um, is not known, but we know on each conductor the charge is the same. The total charge, for example, for the first conductor is A. And let's say there's some specified charge density rho in the region between the conductors. Is the electric field now uniquely determined? Or are there perhaps a number of different ways the charge could arrange themselves on their respective conductors, which leading to a different field? So this is the second uniqueness theorem. In a volume V surrounded by conductors and containing a specified charge density rho, the electric field is uniquely determined if the total charge on each conductor is given. The region as a whole can be bounded by another conductor or else unbounded. Okay, so that's the second uniqueness theorem. If in a volume um, surrounded by conductors and containing a specified charge density rho, then the electric field line is unique. Okay, so here it shows the proof of the second theorem. It's a little bit more complicated. You can go through with the derivatives or how to derive or how to prove the second uniqueness, let's say, theorem. It's a little bit more complicated than the first theorem, but the good thing is you don't have to remember how to prove it. You just need to remember this conclusion. Just keep it in mind. There's a uniqueness theorem for conductors. That's all we need. If you're interested, please go through the equations and the and see how to derive this second theorem. But at least, please remember this second uniqueness theorem. Okay, so this class is easy. So we will finish this class here, and in next class, we will learn something about the conductors. Okay, that's all for today. Thank you, guys. Bye-bye.